Lesson 1.4. Vector transformation of a system of forces acting on a mechanical system. This is lesson 1.4 from the book Mechanical Systems Calculations of the Marine Facilities. It's important sometimes to deduct the system of forces to the simplest form. It's important to decide the balance equations and to determine the forces acting on the mechanical systems, systems like a absolutely rigid body or system of absolutely rigid body, so just a material point. Generally, the system of forces acting on any kind of the mechanical body we can reduce to the resultant force and two main moment, the pair of force. But besides of that, we have a definite set of the particular cases of the reduction of the system of forces to the simplest form, to the resultant or to the moment, such as the first particular case, reducing a special system of forces to a pair of forces. If resultant equal to 0 and the moment not equal to 0, then the system of forces is reduced to one pair of forces. The main of forces in this case does not depend on the choice of the center of reduction. So moment is a free vector. We can move moment in point of the application of moment to any point. Usually the force is sliding vector, so we can slide the force along the line of action. But if the force is equal to 0 and the moment not equal to 0, then the system of force reduced to the moment, to the pair of forces, and the moment acting on the system we can apply to any point as well. That's why the pair of forces which cause the moment, we as well can apply these forces to any of the points of the mechanical system, like absolutely rigid body or the material point or the system of the bodies. The particular case 2, bringing the special system of forces to a resultant. If the resultant of the forces acting on the mechanical system do not equal to 0 and the main moment is equal to 0, then the system of forces is reduced to the resultant force vector R with the asterisk, R with asterisk equal in magnitude and direction to the main vector. The line of action of the resultant variant passes through the center of reduction of the system of forces. So when we reduce the system of forces to definite point, this is the center of reduction. And the line in the direction of the resultant force R asterisk is possible as we can slide the force along the resultant force along this line. The next is transformation of the special system of forces. The case number 3, reduction of system of forces line on the plane. First of all, we need to determine the point 0, 1. So we have the system of forces, which is characterized by the resultant force R and the main moment m0. We need to find the pair of forces which satisfies the main moment m0. The first force we do on the plane is the balanced force with the resultant R. That's why the extend to the next one, point 0, 1, when they apply the force R asterisks. The distance in between these two forces are stroke and R asterisk are equivalent together to the free vector moment which we can apply to any point of this in this plate. So the distance is the magnitude of the force we can consider, and the magnitude of the moment. If we divide the magnitude of moment to magnitude of force, we can perpendicular to the direction of the force R from the point 0 determine the arm of the force R asterisk, which is equal to the distances of m0 dividing to the magnitude of the m0 dividing to the magnitude of the resultant magnitude R. So we can find another point of the application R asterisk of the resultant force, main resultant force. These two forces, this one which is in the couple with R asterisk, the second one R stroke, are the forces equivalent to rotating moment m0, main moment. That's why we took this force R stroke of the same magnitude as the force R and on the opposite direction to the force R. So these two forces are balancing, and together they give us zero force. And these two system of forces originally specified as m0 and R, finally we can deduct to the only one force, R asterisk. This transformation of the special system of forces, reduction of system of line on the plane. Transformation of a special system of forces, the concept of the dynamic crew dynamo. The special system of forces is a dynamic crew dynamo when the resultant vector is parallel to the moment vector. So if the resultant vector parallel to moment vector, which is the pair applied in the same point, we can consider in this system of forces, system of efforts, to be more correct. System of one effort is main moment m0 and the second moment, and besides of the moment we have the force R, resultant force acting on the mechanical body or material point. These two we can assume and consider as a pair of the efforts. One effort is m0 and second one R. As together we say, they lie on the same line. This is dynamic crew, like dynamo. If in particular case 5, the reduction of special system of forces to dynamic crew, we can consider as well if the force like R and specified moment, the main the resultant force and the main moment are inclined to angle alpha. First of all, we have to find the projection of the main moment to the perpendicular axis x, to perpendicular to point 0 of the application of the force, and parallel axis, which is the axis z, which coincides with the direction of the main force resultant R. So the perpendicular projection of the main moment m2, m02, we can decompose into the pair of forces. One is R stroke 1 and second one is R1. So this R stroke 1 we preconditionally making choice to be equal in the size to the R stroke. So this is a balanced system of forces. And that's why only one force remains R1, and as well remains the projection of the axis 0z of the main moment. This is M01, and this is a free vector. We can move to any point of the space of the moment vector. So we move it into the new point of the application of the force R1. The distance d between the points 0 and 01 is the result of the division of the projection of main moment onto x-axis when we divide to the force R magnitude. Then we have to find the arm 001. And these two forces originally specified the main resultant R, and the force specified as a decomposition of the action of projection M02. These two forces, R stroke 1 and R1, are a result of the decomposition of the projection of the moment, main moment on the x-axis. So these two forces R stroke 1 and R resultant are the same magnitude but the opposite direction. They are balanced system of forces. So only force 1 R1 remains here applied on the point 0, 1, and to the same point we move the projection of the moment on the axis 0, z, and we have two efforts directed on the same, having the same direction. This is previously considered dynamic screw, dynamo. So the reduction of special system of forces, the special system of forces, if the efforts like main moment and the resultant are inclined, the directions of these vectors are inclined to each other, we can reduce to dynamo applied to the another point. Transformation of special system of forces. In the next case, if the vector of force and the moment are mutually perpendicular and can be reduced to the same force. For this transformation, so we have originally specified moment, main moment m01, and we have the resultant force R. So can we transform this? Yes. First we find this can be transformed only to one force R. How to do that? First we have to determine the arm D between the point 0 of application of the force and the same the moment specified. And this arm is equal if we specify the balance, the force R stroke 1 for the balance of the assigned resultant. So we can find the arm D dividing magnitude of the moment specified m01 to magnitude of the force R. So we can find the arm D and the point of the application of the force R. And as these two forces R1 and R in the new one point are the same as the decomposition of the moment m01, so we can consider next only the forces, and these two forces R1 and R are balanced, and they together gives us 0 force, and only one force remains R. So we transform mutually perpendicular the force specified R and the main moment m01 to the same force R, but applied to another point located in the distance of the D from the original point of application 0 in the perpendicular direction from the point 0. And let me summarize the general options of transforming the special system of forces to the simplest form is possible. What is the special cases? The first special case, if resultant of the forces acting on the mechanical system, like a mechanical point or maybe absolutely rigid body or system of bodies, if the resultant are 0 and the main moment are not 0, the system of forces is reduced to one pair, and the main moment in this case does not depend on choice of the center of the system reduction. If a resultant acting on the mechanical system specified not 0 and the main moment is 0, the system of forces is reduced to the resultant force only, equal in the magnitude and direction to the main vector of forces. If the resultant not 0 and moment not 0, main moment, and they are perpendicular as the angle between the action lines of the action of the force and the direction of the moment is 90 degrees, the main vector and the main moment are mutually perpendicular. The system of forces is also reduced to resultant force equal to the main vector. And the particular case 4, if the resultant not equal to 0 and the moment not equal to 0, and these vectors are parallel to each other, then such a system can be considered as a dynamic screw, as we assume that moment and the main moment is a free vector. Free mean that it could be any point of the application. So we can just move the moment to the point of the application of the resultant force R. It can be the point of reduction of system of forces acting on the mechanical system. And consequently, we have the dynamic screw. So two efforts, force and moment applied to the same point acting on the same line. If the resultant not equal to zero, moment, main moment not equal to zero, these vectors are not perpendicular and do not parallel to each other, then the system of forces is also reduced to dynamic screw, but applied to another point. If the line of action of the main resultant, like here, special case 5, and a line of the direction of the main moment vector are inclined, so we have to first find the projection of the moment to the plane which in the force lie, and we second projection have to find the perpendicular to the plane where lie the resultant force are. So the second projection we can decompose into the pair of forces of the same size as the resultant specified for the assignment. And this system of forces, we have to decide the point of application of second force. The first applied in the same point where apply the resultant force. So resultant force with the force deducted from the projection of the main moment to the axis perpendicular to the plane where is the main force give us 0, because they are balanced system of forces and only one force remains. And we have finally only the force resultant moved into another point of the application in the perpendicular direction from the point of the original application, and for the distance moved of the magnitude of the projection of main moment on the perpendicular to the plane where is the resultant of the force. We magnitude of this projection of moment divide to the magnitude of force and can find the distance of the relocation of the force point of the application of the resultant. It remains and remains as well the of the same direction free moment of projection of the main moment to the onto the plane where is the resultant force. So we have the dynamic screw, but applied to the another point of the mechanical system. And to this lesson we have different exercises. First of all, we have to specify the data for the exercise. We have 3 exercises. For the first exercise, we specify data. We have the Cartesian system of coordinates x, y, z, and we have forces in the system of coordinates. Force F1, 4 kilonewton. F1 is this force, 4 kilonewton, F2, 3 kilonewton, directed by the diagonal of the this upper plane of the this parallelepiped of the projections. F3, 6 kilonewton applied to this direction. This direction is from the point 1 of the vertices of the projection parallelepiped directed to the point on the other edge of the this parallelepiped on the height of d. We have here specified as 5 meters. And we have force, I also say force 3. The sizes of this projection parallelepiped are CBA, sorry, C 6 meter, B is 5 meter, B 4 meter, sorry, C 6 meter, A 3 meter, and D here we have 5 meter. To decide this assignment, first it's very logical to find the cosines of the angles alpha, gamma. Alpha we have here as well, and the cosine to determine the cosine of this angle, so we must originally found that the distance, this we have to consider the right angle triangles. So as D is 5 meter, the diagonal of this plane rectangle here is 5 meter too, as B and A. B is 4 meter and A is 3 meter. So we use Pythagoras theorem, and we can find that this diagonal is 5 meter too. So the gamma angle is 45 degree, and then cosine of gamma is 0.707. 0.707. Is gamma is 45. It's 45 degree because this is x, d, y, the right angle triangle. This is right angle, and the two legs we have 5 meters. That's why the if two legs is 5 meters, the angle if not right, but it is 45 degree. And cosine of 45 degrees is 0.707. 0.707. The cosine alpha is 0.6. We find this as the diagonal is 5 meter excuse me, the leg A is 3 divided to 5 meter is cosine of angle alpha. Please consider that we do not use the angles themselves usually, but we use the trigonometric functions of these angles. So we use a function of the sine, a function of the cosine. The cosine alpha is a proportion of A to this diagonal. This proportion is A is 3 meter, diagonal is 5 meter, as we can find using the leg B and leg A. This is on the horizontal plane the right angle triangle, and B, this means 4 in the square degree is 16. A is 3 in the square degree is 9. 16 plus 9 is 25, and the length of the diagonal is 25. Square root of 25 is 5. So 5 meter, and the cosine of the angle A mean the A 3 divided to 5 meter is 0.6. Besides sine alpha, consequently, we can find a 0.8 sine alpha, and sine of the 45 degree gamma angle. 45 degree gamma angle, sine is 0.707. So let me please repeat. Cosine alpha is 0.6, sine alpha is 0.8, cosine gamma is 0.707, and sine gamma is 0.772. So having the direction angles sines and cosines, we can next to do decision of the assignment. We have to find the resultant force and the main moment. To do that, first we remind that the main vector of force system is resultant force. We can find this in the vector form as the multiplication of 3 summands. Summands each is a vector. Vector force is projection of the magnitude of the resultant force onto the abscissa axis multiplied I. I is the unit vector of the abscissa axis plus Ry multiplied J is unit vector of the ordinate axis, and projection of the main force on the axis Z multiplied K. K is unit vector of the Z axis. The functions of angles we have here. I explained how to find that. The projections of the main vector on the force on the coordinate axis are the first projection of the main force. We consider consequently each of forces acting on the in the system, and we use the direction cosines and sinuses, and so we find the projections of the forces. The first is minus, consists of 2 summands, Rx, projection of the magnitude of the force on the axis X. We have 2 summands. The first summand is minus f2 multiplied cosine alpha plus f3 multiplied cosine gamma and multiplied cosine alpha 2. So the projection of the axis x, we first consider f1. f1 is lie in the perpendicular plane to the axis x, so the projection, the impact of the f1 on the projection of the resultant force on the axis x is 0. Another force f2 we can decompose into projections parallel to the force y and parallel to force x, but with opposite direction. We use the concept of the cosine alpha. So the projection of force 2 on force on the axis x is magnitude of f2. Magnitude of f2 is 3. Multiplied the cosine alpha. Cosine alpha, we have got cosine alpha is 0.6. So minus 3 multiplied 0.6 plus 6 multiplied 0.707, this cosine gamma, multiplied 0.6 is cosine alpha as well. This because force F3, first we decompose this and project this on the horizontal plane and find the next decomposition, the projection of the force 3 on the x-axis using the first cosine. First we use the cosine gamma, and next we use the cosine alpha. This is final decision. The same we do for each two projections of the forces, force resultant projections on the y-axis and z-axis. The projection of Ry is the two summands. The first is f2, magnitude of the force 2 multiplied sine alpha, and minus f3. First we project f3 on the plane by cosine gamma horizontal plane. Next we project these two on the sine alpha to find the projection of the f3 on the axis parallel to x-axis. Rz is consists of two summands. The first is minus f1 plus f3 multiplied sine gamma minus f1. First we use the force 1 because it is parallel only to the axis z, but have the opposite direction. And these two forces rest. The projection of force f2 on axis z is 0 because it lies in the plane perpendicular to the z-axis, and the projection of force f1 to axis y mean 1 multiplied the arm A, and one is with rotate counterclockwise, so is a positive side, and f1 multiplied arm B rotate clockwise, so projection of excuse me, I'm talking about the moment determination, sorry. We still determine the forces. So finding the forces, main force vector magnitude is the square root of sum of these found three projections in square degrees each. And we can find that the magnitude of the main vector is 1.266. After that, we have to find the direction cosines of the main vector. They are projection of each of the axes to the magnitude of the resultant force. Cosine between the main force and the abscissa axis is 0.588, and cosine between the resultant force and ordinate axis is minus 0.785, and cosine of between the resultant force and z-axis is minus 0.191. Next, we can put it onto the coordinate system of Cartesian. So this R, this is projection of forces Ry, Rx, Ry, and Rz, and finally we can find this projected may resultant on the picture. After that, we have to find the projections of the main moment of the coordinate axis. We generally assume that the moment for each of the projection of force, we multiply to the projection of forces onto the arm relative to definite one axis force. Projection of the force vector m0 to the x-axis is minus f1 multiplied b minus f2 multiplied sine alpha multiplied c plus f3 multiplied sine gamma multiplied b. So if you look on the picture, original picture here, the projections of main moment on the x-axis is this horizontal force is force f2 multiplied the sine alpha, and the arm is c. C is arm for the moment of this projection rotated with the body counterclockwise. The second is the F1 force rotated counterclockwise is F1 multiplied B. And the next is this one projection vertical rotating around the axis X counterclockwise. So is magnitude of force F3 multiplied sine gamma and multiplied B arm between the axis X and the application of the vertical projection of force F3. This is projection of all forces on the, this is of all projections on the axis X of the main moment caused by three forces specified in the assignment. And the same we can find projection on the y-axis, on the x-axis. Generally, we can explain that a projection on y-axis of the force F1 we can find as multiplied force F1 acting on the arm A. The force F do not cause a moment relative the XSY as this force crosses XSY. And the projection of force F2 is a magnitude of F2 multiplied cosine alpha. But it rotates the body clockwise if we watch toward the y-axis. So the this component of moment projection on the axis y is of with a negative sign, minus. And the same we can find projections on the z-axis as well of the forces on z-axis. So on the z-axis force one do not impact on the appearance of the moment relative to z-axis as force F1 is parallel to z-axis. The F3 we decompose first onto the vertical component and the horizontal in the plane by the diagonal of this rectangle, projection rectangle. And this projection on the horizontal plane we decompose next to two components which is parallel to x-axis and parallel to y-axis. But these two components, vertical and parallel to y-axis, cause zero moment relative z-axis as parallel force do not cause a moment relative axis, and the second one, a component of force F3 cross z-axis arm zero, so it doesn't cause a moment as well. So only this projection parallel to x-axis from the force F3 gives us the component of projection of main moment on z-axis. And we do that relative z-axis. After that, we find magnitude of the main moment as square root of the sum of three summands in the square degree first mx found by and mz. we can find that the magnitude of main moment is 13.811 kilonewton per meter. Next, we have to find the direction cosines of the main moment. The direction cosines are we divide each of the projection of the main moment to this magnitude, and we find cosine of the direction angle of main moment vector to the axis x, cosine of direction angle of the main moment angle to the axis y, and the direction of the main moment to the axis z. So this is the decision of the assigned decision of the exercise. Finding of the main moment, main force, and the angles or direction cosines of the angles of the main moment and main force. Second assignment, second exercise, the assigned system of three forces, F1, F2, and F3, bring the center of the point 0. The data is in the table 1.4.2 and on the diagram. So we have three forces F1, 3 kilonewton, F2 is 5 kilonewton acting in the rectangular projection plane perpendicular to y-axis. The force F1 parallel to y-axis and perpendicular to x-axis. And we have force 3. Force 3 directed by diagonal of the rectangle. Rectangle is of diagonal of the horizontal rectangle of projections, and the edge C is vertical direction. So the sizes of the projection parallelepiped are 3, 4, 3, A, 3 meter, B, 4 meter, C, 3 meters. So we have to find the resultant acting of the mechanical system and the main moment acting of the mechanical system as vectors. First of all, we have to find the trigonometric, the meaning of the trigonometric functions of the direction angles. We have to find the cosine alpha is 0.707. This is because angle alpha is equivalent to 45 degree. Angle alpha here, 45 degrees. So A and C, AC, two sides of the right angle triangle. This is like is C 3 meter, A is 3 meters. So this is right angle triangle. This is right angle. So the alpha is 45 degree, and the cosine and sine alpha equal to 0.707. Cosine beta equal to 0.8. Sine beta angle is 0.6. So the beta angle we have here. We do not need the angle itself, but we need the sine and cosine. We have to find first the diagonal. Diagonal B is 4, one leg, and A is 3. So we can find that the diagonal A0 is 5 meter. So the sine of angle B is this h0x divided. The a0h is equal to a 3 meter divided to 5 meter diagonal. We can find the sine beta. Sine beta is 0.6, and the cosine beta consequently 0.8. And as well, we have next angle is gamma angle. Cosine is as first we can find the gamma angle here. We can find it the direction, the length of this diagonal of this triangle. The one leg is C is 3 meter. Another one leg is 0A. It is 5 meter using the theorem of Pythagoras. we can find the diagonals and the hypotenuse of the right angle triangle A0Z. Next, we using the leg and the length of the diagonal, we can find the for the one leg, this one A0, we can find the cosine. If we divide this leg to the diagonal size, this leg is 5 meters. This one, I don't remember how long it is, but we can find it using the theorem of Pythagoras. And the second is the sine of gamma is when divide z0 to the length of this diagonal. So we did find the cosine gamma and sine gamma too. And next, we have to find the projections of the main vector of forces on the coordinate axis. They are the projection Rx on the main force on the axis X. So this projection consists first, the force F1 do not cause the projection on the axis X. The force F3 did first we have find the projection on the diagonal A0 using the cosine of the angle gamma. We multiply F3 on cosine angle gamma, and next we having that multiply this to sine beta. So we can find alpha from this parallelogram of the forces. And this projection of force F3 on this edge AY is parallel to axis X, but opposite direction, so we use a minus. And the force F2. First, we have to use the cosine of alpha angle to find the projection of force F2 into the horizontal direction parallel to X. And this includes here. And for the same for projections of the assigned forces on the axes Y and Z. On the axis Y, we found the force F2 do not cause the projection of the main force due to the F2 lie in the perpendicular plane to the axis Y. The force F3 cause the projection. We first decompose to the horizontal plane. This is, we use the gamma angle, cosine gamma angle. Next, we use the cosine of beta angle. And next, we can find the component of the force F3 parallel to axis Y, but of the opposite direction. And next, we find the projection of the main vector on the axis Z. The projection of the axis Z is like the same way the force F1 do not cause the projection of axis Z because it lies in the perpendicular plane to the axis Z. The force F2 first we decompose into two components, one horizontal, one vertical. This vertical cause the projection of the force on the axis Z, but with a minus sign. And next we have to find this projection F3 impact on the resultant projection on the axis Z. We multiply magnitude of the F3 on the sine of the angle gamma of this right angle triangle, so we can find the projection on the Z axis. This way we found three projection of forces. Forces projection Rx, Ry, and Rz is 2.507 kilonewton. Ry is 1.629 kilonewton. Rz is minus 2.507 kilonewton. The magnitude of the main vector force is square root of the three sums of the sum in the square degree each of the projection of the main vector onto the axis of coordinates of the Cartesian system of coordinates. Next, when we found the magnitude of the main force, we can find the cosines of the direction angles. The cosine of the angles R when we divide each of the projection of the main force on the main force magnitude. So we have three cosines. Cosine of the projection of main vector on the x-axis and this main vector, and cosine between the main vector and the y-axis, and cosine between the main vector and z-axis. After that, we have to find the projections of main moment on the coordinate axis of the Cartesian coordinate system. We use a decomposition of the action forces specified, and we use the arms we have. So first, we have to find the projection of moment of main moment on z-axis. Force F1 do not cause the moment because it intersects x-axis. I do not cause the projection of the moment on x-axis. Force F3 cause the moment because cause the projection of main moment on x-axis because it have horizontal projection when we decompose, and it has applied in the point horizontal projection, and besides the force F3 have the vertical projection, the vertical applied on the same point. The vertical can find using the sine gamma, and horizontal we use a first double decomposition. First the cosine gamma, next the sine of the beta angle. So the force F3 impact on the projection of the main moment on x-axis is this one force, and as F3 magnitude multiplied cosine beta multiplied sine beta, and oh, I'm sorry, this one do not cause the moment relative x-axis, as this one direction is parallel to x-axis. So, and this one as well do not cause only vertical cause. The vertical cause is a multiplication of force magnitude F3 on cosine gamma. Sorry for my mistake. It acts applied in the point A, and arm is B, rotate counterclockwise, so we have the positive sign. And the force F2, the horizontal component do not impact the magnitude of the main moment projection on x-axis, and only we have vertical projection. This vertical projection equal to the magnitude of F2 multiplied sine alpha. And the leg is, I'm sorry, arm is B, and the direction is negative because it rotates clockwise if we look toward x-axis. So this way we found the projection of main moment on x-axis, which is minus 10.028 kilonewton per meter. No per meter, product meter. And by projection, we can find the same way, but relative y-axis. Relative y-axis. Relative y-axis, this component force do not cause the moment because it cross axis. This F1 do not cause the moment because it parallel to axis. On these two components horizontal of the force F3 do not cause the moment because they first intersect axis, and the second one parallel to the axis. On the vertical is magnitude of F3 multiplied sine gamma cause the negative moment with the arm A negative because they rotate the body clockwise around the y-axis if you look toward the gamma direction. Only F2 multiplied cosine alpha rotate counterclockwise with the arm C, and F1 do not cause the moment. So we can find the projection of the main moment relative to the gamma axis and relative z-axis, applied axis of the force 1. This rotate counterclockwise if you look towards it, and F magnitude we multiply arm A this F3 cos only by the, oh, sorry, by to this component on the horizontal. So F3 first we decompose to component of F3 magnitude on the horizontal plane by the cosine gamma, and next we multiply cosine gamma magnitude of the force F3. Next we use the cosine beta to find this component of force F3 parallel to y-axis, and we use the sine beta multiplying this one diagonal projection of force F3. Using sine beta we can find this component parallel to x-axis. Considering the direction, we can use arm. The second case is B, for this horizontal is A. And the vertical applied here, it gives us zero projection of the moment of the vertical component relative to z-axis. So we can find as well all components of main vector relative to axis x, y, z, relative axis x. We have the component we told minus 10.028 kilonewton by meter. Relative y-axis 7.5 to 1 kilonewton by meter. Relative z-axis is minus 5.14 kilonewton by meter. So using the Pythagoras theorem, we can find the magnitude of the main moment is a square root of the sum of three components in square degree each. Finally, we have the main moment magnitude 30.548 kilonewton by meter. And we next have to find the direction cosines of the main moment, the directional sign. If we divide each of the projection onto the magnitude of the main moment, we can find the cosine between the main moment and the abscissa axis x. We can find as mx divided m0 is minus 0.3740. Cosine between main moment and ordinate axis is my divided m0 is 0.555, and cosine between the main moment and the applicate axis is minus 379. So next assignment, exercise 3. The sign system of three forces, F1, F2, and F3. We have to bring this system of forces to the center point. The data indicated in the table 1.4.3 and on the diagram, the table 1.4.3. So we have forces F1, F2, F3, F force 1, 5 kilonewton, F2 is 5 kilonewton, F3 is 5 multiplied square root of 2 kilonewton, and F1 we have here, F2 we have here on the diagonal on the right rectangle perpendicular to y-axis. And the sizes of the projection parallelepiped are the first size A is 6 meter, B is 10 meter, C is 8 meter. So first we have to find the cosines of direction angles. Cosine alpha is 0.6, cosine alpha is 0.8, cosine gamma is 0.707, and sine gamma is 0.707. Gamma, we have the angle gamma here. Here is 45 degrees. To understand, we have to find two legs. We consider the right angle triangle here, this right angle here, and the legs of this triangle is B. B is 10 meter, 10 meter B. A and B 10 meter, and X, Z leg size. We use the Pythagoras theorem. So one, in considering the this like a diagonal, this rectangle projection on the left, and this consists of right angle triangle. This is right angle 2. This leg is A is 6. 6 in the square degrees 36. The C is H in the square degrees 64. So when we sum 2 square 6 in the square degree plus H in square, we have 100. And when we find the square root of the 100, we can find that the distance of x, z, this diagonal is 10. So we have a right angle triangle here is a right angle. This leg is B10, and this leg is 10, 2. So this angle gamma is 45 degree, and the cosine and sine of 45 degrees 0.707. So that's how we found the direction angles, sines and cosines. Next, we determine the projection of the main vector of forces on the coordinate axis. Rx, Ry, and Rz. Rx, first we of the force F1 projection is 0 because this force line the plane perpendicular to x axis. This we have only the projection of F2 on the horizontal line of the projection. So we use the cosine alpha. So we multiply F2 cosine alpha. Next, we use to double decomposition of the force F3. First, we decompose this to the left side rectangle with the projections. And next, we decompose the God projection of F3 force onto line parallel to the z-axis and onto line parallel to x-axis. So to find this diagonal projection of the force F3, we use the gamma cosine, and next we multiply the magnitude of force 3 on the gamma cosine and can find this left side projection of F3 force. And after that, we multiply this on alpha cosine, and we can find the projection of F3 on the force x. And if we use the sine of alpha, we can find the projection of this previously found projection of force F3 on the diagonal of the late rectangle projections. We can next, using the sine of alpha, we can find the vertical component of F3 force parallel to z-axis. And we determine this as a sum, double projection of force F3 and one projection F2, and F1 do not cause the projection of force on the axis X. On the axis Y, the force F2 do not cause projection as it lies in the plane perpendicular to Y-axis. F1 is in the projection of the force on the Y-axis with a minus sign, and F3 is on the projection on the axis Y due to the sign of gamma. So the magnitude of force F3 multiplies sine gamma. It is as well in the total when finding the projection of the main vector of force on the y-axis. RZ. So on the applied axis, first we do not consider F1 because it is in the plane perpendicular to z-axis, and we use F2 multiplied sine alpha, finding the vertical part is the same as z on the axis z with minus sign because directed to the opposite direction to z-axis. And we consider F3, and first we project it by the decomposition on the diagonal of the left side rectangle projection using the cosine gamma, so magnitude of 3 multiplied cosine gamma, and next we multiply this on sine alpha, and we can find direction of the component of F3 force on parallel to z-axis. So next we can find the, as all projections are zero, we can find that the main force vector model after the substitute of the meaning of each of the component in the calculations. We can find that all projections are zero. It's not important, zero what? Kilonewton or other unit of force, just a zero. So the resultant is 0 too. After that, we have to find the projection of the main moment of force on the coordinate axis. They are so relative axis x, the moment of force F3 is 0 because F3 crosses the axis x. It don't cause the moment. The force F2, the moment caused by this vertical component of force F2 is this magnitude of the force F2 multiplied sine alpha. We have the vertical 1 and it rotates clockwise, so minus sine, and we multiplied the arm B. The horizontal do not cause the moment of main moment relative to the x-axis. And the force F1 causes the moment positive, and arm is C. The moments relative to the y-axis of the force F1 is 0 because it's parallel to y-axis. The force F2, only this one horizontal component of F2, because the moment is positive. We found the magnitude F2 multiplied cosine alpha and multiplied legs C, positive because rotate the point counterclockwise if we look toward the y-axis. And of the force F3, we have components located in the parallel. They do not cause the moment relative x-axis. And we have the component only here, only vertical one, because this horizontal component crosses the axis. This after second decomposition of force F3, this one component we decompose it's in its turn into one horizontal and vertical. The horizontal do not cause the moment because it crosses the axis y. This vertical component cause the moment negative because rotate clockwise, and the arm is A. So magnitude of F3 we multiply cosine gamma found this diagonal first decomposition diagonal component of F3 force, and next we multiply sine alpha, this angle between the force component in the left rectangle projection on the picture, and the horizontal axis alpha we have here. So we have only this one. So F3 magnitude multiplied cosine gamma and multiplied sine alpha, and this is negative moment relative to y-axis because rotate the clockwise. If we are talking about the moments relative z-axis, first we have to indicate that the force of one rotate counterclockwise. Oh, sorry, rotate clockwise, and the arm is A of force F1. The force F2 decomposition on the horizontal component caused the moment relative z-axis because the vertical component is parallel to z-axis and do not cause the moment relative z-axis. So F2 magnitude multiplied cosine alpha rotate clockwise relative z-axis. This cause negative moment as well. And the arm is B, or this force F2 component horizontal. And only this component is F3 magnitude multiplied sine gamma. Here we have on the horizontal edge B cause the rotation moment relative z-axis as this line, and the one is in the plane parallel to z-axis. One is parallel to z itself, but another one cross axis z and cause zero moments. So only this one. So magnitude of F3 multiplied sine gamma, we can find this one leg, this one leg is equal to this one, and it rotate counterclockwise relative z-axis, so have this component impact on the projection of the main moment relative z-axis with the positive sign, and the arm is A. So after the substitute of the meaning of the forces and legs, we can found that the projection of main moment of the x-axis 0, projection main moment on y-axis is 0, projection of the main moment on z-axis is minus 30 kilonewton by meter. And exactly, we do not use the Pythagoras theorem to find the magnitude of M0, which is equal to one of the components as other two are zeros. And the questions and comments. Conversion of the special force system to a principal vector and force pair, to the main vector and force to the pair. So any system of forces we can convert to acting on the mechanical system like a material point or the absolutely rigid body or system of absolutely rigid bodies. We can deduct to acting one force is the main resultant, and to the main moment, this principal vector and force. Reduction of the special force system to force pair if the main vector is 0. Yes, if only the moment acts on the mechanical system, so this only one moment is effort acting on the mechanical system. Reduction of the special force system to resultant if the moment is 0. If moment is 0, it's only force is acting on as two efforts. One effort is force, another one is a moment. So if moment 0, only force acting on the mechanical body, we do not need to reduct to reduce to next reduce after finding this force, or after find the moment if the rest effort moment of force are zeros. Reduction of forces system line on the plane. We have for the forces system line on the plane the special cases. If only if the main moment is free vector, so point of application can be any. The force is sliding vector, the point of application is on the line of action. So we can usually reduce to of the action of the force to dynamic screw. Dynamic screw is when the free vector of main moment we coincide with the point of the application of the force, and this is we can transform in the manner when the main moment and the force have the same direction and applying the same point. And to we say this is the concept of the mechanical screw, the torsion, reducing the special force system to a dynamic screw. To reduce the special force system to dynamic screw, we usually use the concept of the balance forces. So if you have the force, main force acting on the mechanical system and the main moment, so we decompose the main moment into the pair of forces and one of the same magnitude as the main force. But we decompose the main moment in the manner when the couple of forces, pair of forces, when one of the forces in the pair and the second one exactly are of the same magnitude as the main force, and we coincide as the moment is a free vector. We coincide the point of application of one of forces of the pair as a result of the decomposition of the main moment. We coincide with the same point of the application with the assigned resultant acting on the mechanical system, and acting opposite to the assigned resultant acting on the mechanical system. And next we have by the same plane of perpendicular to the line of action of the moment, we have to find the distance of the application of the second force of the couple of the decomposition of the moment. So the first couple of forces, the main force assigned on the mechanical system and the force deducted from the decomposition of the main moment are the balancing system of force, and only one force remains is the force of action of force or the second component of the composition of the moment applied to the main moment, and only remains finally two efforts: the force resultant put in the another one point, and the component of the moment of the main moment assigned, component parallel to the force assigned, to the main force assigned. Thank you.